There you go. Okay.
I got two more. Are you going to get? Okay, you are eating. I'm going to eat too. Get this. Sorry, that's okay. It could be yours. All right, 10. I only prepared 10. How's Jackson?
All right.
All
We'll
right.
just do the one.
Should I start?
Oh yeah, sure.
Oh, it's up here. I can start.
Yeah, and then I usually do this
I
thing where I go up here.
I don't look like a professor. I know.
Yeah, well, here we are, sir. This is it. Hello, everybody. I think you all know why you're here. I'd like to introduce Dr. Feng of the Research Feng Group. If you want to come up and introduce yourself.
Oh, yeah. Hello, everyone. My name is Yuanning Feng. I'm a new assistant professor here. I just joined OU last August, so I'm really new. I'm newer than you guys. It's really my privilege to be invited by the chair to join the OU math club. I really like math when I was a kid. But it turns out I moved to chemistry because I have a good friend who really good at chemistry. He wanted me to join him to get the chemistry Olympiad together, and luckily I got the gold medal. So that's my story how I joined chemistry. But still I love mathematics. And you want to know more about me, and it's more importantly my group, look at that, right? And also scan the QR code, you'll find something fun. And today my talk is about the relationship between chemistry and topology, which is a subject in mathematics. And I would like to, I use a title called Tying in the Tiniest Nodes and Weaving the Thinnest fabric. And you will figure it out very soon. Luckily, I have two excellent students, Jackson and Luna in the back, who are also interested in the relationship between chemistry and topology. And they are really great to help me to present together. I also consider us a part of training for giving presentation. So please join me to welcome Jackson first.
Hi, everybody. I'm Jackson Lancaster. I'm an undergraduate student at the University of Oklahoma studying biology. So, before we get started on topology, we have a quick activity. Everyone was supposed to get one of these, but the taping did not really want to work out today, so it'll be a class demonstration instead. So, what we're going to do is, we're going to cut right here in between these two lines, and I want you guys to think about any predictions you might have for what happens when we do that. So, because it's going to be another minute for you to cut.
What's the prediction?
Huh?
What's their prediction?
Does anyone have any predictions for what might happen when I cut this in half? Because it's essentially just a piece of paper that we flip over one side and tape together. Okay, let's take yes. Yes. So you said two separate loops? Okay. Alright. Here we go. We have one longer loop. Alright. Now we're going to do the same thing again. Does anyone else have any predictions for what will happen this time when we cut it?
One longer.
It'll get longer? Okay, okay. Let's see. Or Jeopardy music in the background.
You should play Bach.
Yeah. Whatever helps you relax, man. Almost there. And, well, okay. We have two interconnected loops. Now, what this activity is supposed to show you is about the focus of topology. We don't care about the shape, the length, or the twisting of these segments. The only thing that we care about is the actual connection between those two segments. And that's why there's a famous saying, actually, about a donut and a mug, and that a topologist cannot tell the difference between the two, because all we care is about the loop and what's actually attached to that loop. So, oh, okay. So, now to bring this into a real-life application, we have the seven-bridge problem. Essentially what it is a river, a big island, and a small island. As you might guess, 7 bridges. 2 on each shore connecting the big island, 1 connecting the big one to the small one, and 1 bridge from each shoreline connecting to the small one. So, this actually brought up a good question from the locals. Can each bridge individually be crossed without repeating one of them? And then came along Leonard Euler, famous Russian mathematician guy, super smart. He drew this, so not just 2 dots, but this is our shoreline right here. This is our big island, and this is our small island. Now, this goes back to our previous demonstration of showing the connections between the things and not the actual characteristics themselves. Because here, our small island, we have 3 bridges, one from each shoreline, one from the big island. Then, these represent the 2 from each shoreline, and then again, the big bridge, small bridge. Now, this is important because not only did it help us solve this problem, but it helped us deconstruct this problem into this, where we don't care about the shape of the island, the size, only the connections between the dots and the lines representing the bridges and the islands. Now, the overall answer to the question was, no, you're not able to do it, but this is a much easier way to visualize this than having someone walk over all these bridges or showing all shapes. Now, to our next activity. Now, you ready? All right. Okay, see if I set this up. All right, here you go. Nice, sweet. Okay. First time to charm on this one. Okay, sweet. So, what I've done here is I've interlocked these 2 segments. And our goal is going to be to separate these 2 segments without having our hands leave these loops or breaking the segment itself. So do you have any guesses on how to separate this?
Only way that I can think of is to like step over and into that.
Yeah, okay. And we'll just go ahead and say it doesn't work. That sounds like a lot of work. So, we'll just go ahead and say no, that doesn't work. So the manipulation. Hold on. This will work. Okay. There we go. There we go. Hold on. Hold on. Let's see. Does it work? No, it doesn't. But let's try it again. Okay. Okay. Try again. Oh, okay. Hold on. I think I'm cooking now. I'm cooking. No, it doesn't work. But okay.
We'll try again.
Try again. Okay.
Yeah.
Third time's a charm. Third time's a charm.
From the beginning.
Okay. Okay. Here we go. Here we go. Here we go. Okay. This on. Okay. 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 Here we go. So we're going to.
I'm not moving my hands.
Oh, trust me. Yeah. Okay. And then. Okay. Well, that's not going to work apparently. But what was supposed to happen was that
This worked Friday.
this worked Friday in the
That's all
presentation. Yeah. So essentially what was supposed to happen was that we're supposed to separate the 2 without breaking one of the segments. And that's very important in topology because those are mechanical interlocking. Now, to further that point, since we have a magnet, I'm just going to hold this up. This is our daisy chain. And this is another example of mechanical interlocking. Because what's holding this chain together is a stopper and a ring. Now, our next example is.
Okay. You need to move the camera, right? So you can put it here.
So right here is our rotaxane, because okay. So right here is our rotaxane, which is essentially the same thing mechanically interlocked because it is 2 stoppers and 1 center ring. Now, our one different structure is going to be our Hopf link. Now, this one is different because these are mechanical interlocking, meaning that we can manipulate these structures to separate our 2 segments without having to actually break one of the segments. This one is different because this is our first example of a topological structure, meaning that we cannot separate these 2 segments without having to break one of these. Now, also, these segments go into more than just, these structures go into more than just one segment, because we can have another example, like this, which is essentially the rotaxane, that's just 1 stopper and 1 ring. And then we have a pretzel, which is our Hopf link, that's also just 1 segment. Now, again, this one is mechanical interlocking because we can make this stopper smaller, or we can make the ring bigger, and that way we can separate the 2 ends. Then this one is just essentially the Hopf link with 1 segment, so basically you can't separate them unless you break one of the segments. Now, this difference between our topological structures means that we need a classification system in order to differentiate between the structures. And each of these contains 3 components. The Y component is what we previously discussed, which is going to have segments in each of the structures. However, the X component is going to be the most important, that's why it's the biggest, and that is going to talk about our amount of crossings in each. So, this right here, our old friend the Hopf link, he has 2 crossings and 2 segments. Then, our friend, Solomon link, also has two segments, but it has 4 crossings right here. And then lastly, our Stoddart David link has 6 crossings, so 1, 2, 3, 4, 5, 6, and also has 2 segments. So this is why we have that X component, because once you see a structure like this compared to this, it gets very complicated very fast. Now, lastly, our Z component, which is these back here, is going to be an index number. Now, obviously, you look at this structure is not very complicated, so you don't really need the Z component. However, when you're using something like a boramine ring and a 3-catenane ring, this can get pretty complicated pretty quick. And so, the difference between these is that this one is a boramine ring, and cutting one of them essentially separates all 3 rings. Then, we have the 3-catenane ring, which, cutting one segment, still leaves 2 interlocked. So, this means you need to cut 2 segments in this structure to separate all 3, while in the boramine ring, you only need to cut 1. And this is why we have that Z, because seeing this towards something like this, that would be the boramine ring, is much easier to differentiate between, than this. And so this allows us to quickly identify the qualities and characteristics of that topological structure. Now, to continue this lecture, I have my lovely peer, Luna.
Hello everyone, I'm Luna. I'm a student from China, majoring in chemistry. And I'm a junior undergraduate student. I'm going to be there for 1 year. And this is my first semester. A little nervous, right? And we introduced, my part is about molecular nanotopology. And what is nanotopology? We know that chemistry plays molecules, and molecular nanotopology studies the interaction between molecules and their topologically structures at the nanoscale. Nanoscale. Everybody know nanoscale? It's about, this. Yeah. And so why do we need to apply molecular nanotopology? The answer to this question is quite in front of your eyes. Let's take a closer look at this structure. And in simple terms, they all possess both stability and flexibility. In the diagram, we can observe that it composed of 2 or more parts. When examine these parts individually, they are all stable and rigid structure. But when topically combined, they can move relative to each other while remaining remarkably stable and not easily disrupted. As we all know, structures determines function. So the unique arrangement can bring special functionalities. And for instance, it can be utilized to in molecular mechanical devices, molecular sensors, smart materials, and more. And consider rotaxing this one as an example. Rotaxing molecules with its ring structure can rotate or move like mechanical gears in molecular machines. And this mechanical movement can transmit energy, perform special functions, or drive the movement of other molecules, molecular components. Moreover, these structures can also be designed with recognition properties by controlling the. I'm sorry.
what's the next part? Sorry. Oh, enabling them to interact with other molecules. This can be applied in molecular recognition, separation, and capture, contributing to the development of molecular machines with desired functions. And lastly, it can be enhancing to make molecular transport canals or systems by controlling the movement or position of the rotating molecules. We can the selective transport or delivery of other molecules can be achieved, which will be applied in fields such as nanotechnologies and drug delivery in the future. Also, molecular nanotopology can also use in catalysts. Catalysts requires the ability to react or form the chemical bonds, facilitating the reactions while promptly detaching to prepare for catalyzing the next reactant. And it demands the requirement to chemical size to be not too tight nor too loose. And I will give an example. It's a catalyst named pentyl foil. And this circle presents ions. And with this circle and this topological structure can't be too loose, but the space there can contain special atoms, and it will help them to cut the chemical bonds. And for instance, this catalysts are really good because it cannot be too tight to binding the reactants to hinder their release. In summary, molecular nanotopology has the special structures, and this can bring about the special functionalities, and it holds the significance for understanding the relationship between moleculars and its properties at nanoscale. And it also can developing the new nanomaterials and addressing the current scientific and engineering problems. And thank you for listening, Jackson and me, the presentation, and I'm really nervous. Thank you. And welcome to Professor Philp.
Okay, Dr. Fraser, student, thank you both very much. Yeah, I hope you enjoyed their talk. They actually practice a lot. I really cherish the time to practice with me. I think they grow during the training, right? And the presentation today. I'm windy guy. Anyway, so in summary, you see in chemistry, we also want to use those topological complex structure. Why? Because in nanoscale, as Luna just mentioned, it's completely different. You probably know why, right? In microscopic world, which is our real world, the domination is gravity, friction, and so on, right? So if you want to make something, let's say, topological structure or a molecular machine, you just make it, right? You make two rings together, you prepare the third ring, come here and glue them. They will not move at all, right? It will stay there as a result of gravity. But as you know, someone know Brownian motion or whatever in macroscopic scale or nanoscale, they are moving crazily, right? They cannot stay still. We have a quote so-called swimming in molars and walking in hurricanes. Maybe here tomatoes. They use hurricanes. Anyway, that means everything is moving. You cannot hold something still. But by using either the topological complex structure or the mechanical interlock molecules, you can maintain them being interlocked together. But why we want to use those structures, they still have the flexibility, just like Luna said. You want to have something function, not just a normal ring or linear shape. You want to have relative relationship moving, changing between those components. That's why you want to introduce the mechanically interlocked molecule or topological complex structure in chemistry, specifically in nanoscale. So that's actually the summary. Why we want to use those fancy structures in nano-world. Then, echoing in the title, how do we make those tiniest nodes? They could be really tiny. They have a Guinness record if you check online. But how do we make them? Since I told you the difficulty, we cannot control them just by using our hand or our machine arm. But we have something. We have binding in chemistry, right? Binding means something can selectively connect with each other or get closer to each other in another word. So if we want to make a node, we can make something simpler. I haven't used chalk for a long time, but I can still know how to use it. Oh. So if we have an ion, something can bind it, right? For example, that's a linear segment, and that's another linear segment. If you have some, let's use this as a binding recognition site, it will bind with the ion. You can probably draw more like this. You might see that on a chemistry textbook. If you are not majoring in chemistry, or even you are in majoring in chemistry, you will not like this textbook. I heard about that before. But if you design those segments well, you are able to achieve some structure like this, right? And the other one goes to this way. This one is not topological complex structure. It's still one ion in the middle and two segments at the two sides. However, we are able to form a new chemical bond by connecting the tails. And you might tell there's highly possibility they form a hot link or two cation. That's how you make a topological structure in nanoscale. This is one of the simple examples, and we can even design a further complex structure so that we can achieve further complex molecules. For example, if we have two ions and we have a longer linear segment, I just draw like this, and we can have a second one which is intertwined with the other one, right? And what happens next? If you connect those two together, who knows what's that?
Kermit with goggles.
Oh, it is actually one segment compared with this, right? Don't count the ions. This is This is 2 to 1 based on Jackson tell you the denotation, right? 2 crossings, 2 components, and index number is 1. But this, you look at that, how many? 3 crossings. 1, 2, 3. How many segments? 1, because it's actually connect back to itself. It's a full loop. And this is just 1 segment, right? And there's no index number for this because this actually simple as a trifoil node. You can still write 1, since it's only 1 segment, usually the superscript y will be erased, like 3 sub 1. That is the topological denotation of a trifoil node. I might bring a trifoil node somewhere, but anyway, you can play with that. And what's next? If you want to have something more complex, you can increase the length, have another ion, and get this. And what's this? You can tell me by denotation or the name if you still remember, because Jackson mentioned that before. It's all right. 1, 2, 3, 4. So the X should be 4 crossings. How many segments or components? So if you go from here, this is 1, and the other one is not connect with that. So there's 2 component or segment, An index number, by the way, is 1. You can't tell index number because that's a chart, right? You need to memorize if you are a mathematician in this major. So this is actually a solid ring, if you remember that. If you go further, I can tell you that will be 5, 1, which is a pentafoil now, just exactly the same as this, the topological structure. If you check it, 1, 2, 3, 4, 5, if I have one more here, will be also 5 crossings. So that's how chemists make those topological complex structure. And this called linear crossing template. There are also some other name, but that's one of the names. That's just one of the methods. We have way more different methods. You can tell this method is not very efficient. Why? I connect the chemical bond just by my chalk. But chemical reaction is really complex, right? You cannot really easily control this one connect to that one instead of going back to that one, right? It's, as I said, it's working in the hurricane, you cannot control. So we call this statistic synthesis, which means it only have a really low yield. However, we can have some other strategy to synthesize those molecules, which is much better. I can draw you somewhere. Let me draw you here. Do you have any idea how do we improve this? This is considered as a linear, right? Something is not linear. You might just use another dimension. If that's one dimension, you might use 2 dimensions, right? If you check this, this actually gives you some hint. We call it a cross-linking connection. For example, you can have a linear segment here. Simultaneously, you're applying metals, right? So I won't draw those T's, but that you got it. When I draw something closer, means there's a binding in chemical, right? And you can also apply something similar, right? And you guess what? I'm about to draw lunar structure. If you have 5 of them, and you have enough numbers of the linear segment, the way you want to connect those is just connecting the adjacent chemical bond here. That gives you a much higher possibility to connect those bonds rather than, hey, all the way go far away to get those chemical bonds. Furthermore, if you look at one of the structures they show you, I'm not going to draw again. Those give you the hint. At those crossing section, they actually used to have metal ions there. So you can even synthesize some molecular bromine ring in chemistry. So back to 2004, my PhD supervisor, Fraser Stoddart, and co-authors just published a paper about how do you synthesize a bromine ring in the nanoscale, which is amazing at that time. Nowadays, including pioneer Professor David Lee in the UK, they have already made so many complex structures. One of the complex structures called 819 ring. 819. 819 is a knot. That's why you don't have Y, because Y is actually equals to 1. But 19 means there are 18 different topological structures have a crossing number of 8, which means, hey, it's not easy to get one, right? You can have so many competitors, but finally, you can only want this 19th ring. So you can imagine how intelligent they design to specifically synthesize the ring. I can draw you the structure, but I'm not going to do that now. Please Google that. I think they have so many news items or even YouTube videos showing the structure of 819 rings. Another example will lead to the second topic is waving the thing in the fibrate, is that, hey, there are 5 crossings, there are 8 crossings. How do we increase the crossings, right? If you consider this is loop, yeah, 5 is fair enough. 8, maybe too very crowded, but what about 9, 10, or 11? You cannot imagine, oh, a full circle, there are 9 ions, and you are going to interweaving whatever around it. It's really difficult. How do you increase the crossings numbers X here in chemistry? Think about that. Hint is here. increase the dimension again. So although this is one dimension, two dimension, you might want another dimension. It's not three dimension, by the way, but it's close. It's called network. So even though I draw, that's the hint, right? You are using two dimension, but still you are applying a loop shape. The real two dimension is network. For example, if you have this 3 times 3 networking and all the ions, and think about how you're going to do that. That's how you do interweaving if you have that, that, and that, right? When I draw linear, it means the component, right? You have a binding with those ions. What next? You can also do that, right? That's the real 2 dimension, right? So now you have 6 segments. Again, iron don't count, right? You count them, it will be 15. And what you do? If you follow my lecture, you will tell you are going to apply chemical bond between the closest segments, right? I'm drawing that and that, right? And I didn't use the slide because I tried to use this method to give you a good demonstration. Okay, if you connect those tails by chemical bond, which is actually can do that, what you will have? First of all, is that a link or a knot? Knot means one component, link means multiple components, by the way. Okay, let's do that. I will start from here. Go down, right? U-turn, go up. U-turn, go down, right? What next? Go here, right? Well, let's go left. U-turn, go. U-turn, go. And that. So the answer is, it's a knot, not a link, right? How do you denote that? You don't need to tell me the index number, but what's the x? Please.
1.
1? No. X is how many crossings?
9.
Okay. 1, 2, 3, 4, 5, 6, 7. No, not 9. Wrong. Why? That's the trick part. Why is not 9? Jackson don't know. I never leave them to go. Yeah. They have no time for me to practice. That's why they don't know what I'm going to talk about. I have no idea what I'm going to talk about either. Why not 9? Think about what he said. Topological structure is about you can manipulating the relationship without breaking them. But there are 2 fake crossings in this figure. Where you can easily twist it, and those 2 connections will disappear, right? Those 2 are the fake crossings. So the x here will be 7. I just draw 7 really big. What's the y? Y is 1. I don't need to. Yeah, y is 1. 1. I just do a bracket because you don't need to write down y again. It's that's enough. What's the index number? It's in my brain. It's full. Read the paper. Okay. Why I draw that? Because that's how you make chemically, right? You will still have a crossing if you have metal ion, but if you demetallize, which means remove the metal, this crossing will disappear. But if you draw that way, if you're familiar with Chinese culture, that's called Chinese knot. You can even Google that, Wikipedia, they call Chinese knot, which that's what they actually published. And by the way, the first author is also a Chinese, my good friend. But think about, they could have some byproducts. Byproduct means some unwanted product, but still exists in running the reaction. What are they? You can tell by erasing those chemical bonds that I draw ideally, right? And change them, right? For example, this will keep the remaining the same, but rather than go that way, you might go this way, right? That could happen, right? You cannot control very well. And similarly, you can have this, right? And you kind of stop being have some others, right? Have other connection. And this will give you what? I can tell the answer quickly. What's this, if you remember? Solomon ring. That is a Solomon ring, right? If you want to draw, you're a mathematician. Go to one, right? What else you can have? You can have some others, right? Even a simple ring. I won't draw them all. But as you can see, this strategy gives you the access to a really complex node, somehow complex links, and so on. That's how we chemistry makes. And then you need to separate them or isolate, right? We call purification because we kind of assuming we really want that, but not wanting that. But you can tell, we call the molecular weight are different, so we can separate them. You just think, oh, the size are different, so we can separate them. Then this portion will be the pure 7-fold link, 7-fold knot, and this portion, which is smaller, but it comes earlier or later, is a Solomon link, and so on. You can even have unknot, which is a simple not-intertwined structure. And that's how you tie the tiniest knot. What about within the thinnest fabric? Any hint? How do we weave a fabric actually? Back to ancient time, 10,000 years ago, maybe not that early, 5,000 ago, when do we invite those clothes fabric? We have, first we use hand, right, to use the needle, go up, down, or finally we invent some machine going that way and change, right, everything up, down to up to down, and going back, right? That's how we work on it, because we can control the motion of the moving parts, right? I should know that English word, but I'm not a mechanics, you probably know that, right? Moving back and forth. But in chemistry, we cannot do that. There's absolutely no way you tweaking that, intertwining through those molecular segments, stop there, turn around, change the up to down, down to up, and come back. There's no way. That's impossible. But how? We got the recognition side, right? We got ions, we got other driving force, or we call it supramolecular interaction, and we can maintain this structure. Okay, think about it. If we don't cross-linking those chemical bonds, what do we do? We do something called intermolecular. Inter in English means between something, right? Intercontinental or international means multiple nations, right? This making knot is intramolecular, means within a molecule. But if you have another structure, right? I need some time to finish the drawing, but not too long. Right? I'm making another one. Okay. In chemistry, the easier way to make billions or trillions of same thing, right? Because we are in a nanoscale, you can easily, it's not even duplicated, we just have so many molecules in a reaction vessel. But my students know you want to control something, right? Making polymer or not making polymers, right? If you want to make a fabric, you want to make a polymer, which means you're connecting the same component together. So you interconnect there, right? 3 of them together. And I won't draw them again, but if I have a computer, I can make an animation. But you will see this. Wow. This is one of the building blocks. Well, actually 2 building blocks combined as a double building block in a thinnest fiber, in a molecular fiber. And that can go on, and you can tell those linear segments, it's extremely long by the way, are interweaving each other. And that is a fabric in nanoscale. That's how you make those fabric. You can even have some other way. If you have an imagination of 3D, I'm going to draw a tetrahedron structure. You have a metal ion here. You are having that and having that. Can you imagine the tetrahedron, right? Do I need a dash line for you to help? Yeah, that's a tetrahedron, right? Okay. And you can duplicate this structure. If you remember diamonds, right? Diamond is nowadays cheap, thanks to chemists. Not that expensive. right? Diamond structure is like that, right? You're just repeating this tetrahedron building block. That's why it's so strong, right? So hard. But by replacing each covalent knot into those topological knot, right? Or not that knot, but that knot, right?
Not.
Yeah, no. Oops, oh my writing. Yeah, it's the knot, not knot. Also a knot, right? Yeah, okay.
No.
And you can duplicate that. For example, this one going to that, and you will have that. This one, oh my God, this will go with that, and this will go that, and simultaneously this will link to that, and so on. It's a 3-dimension. I can't draw them further, but you have your imagination. And that's another way to make them. So you can see you have 2D strategy, and eventually you will have 3D strategy to making the fabric structure or interweaving structures. What else? What else you can apply for those interweaving structure or weaving the thinnest fabric? This is a whole brainstorming section rather than knowledge center. Those are all public. Those are real scientific papers. This is in Science, right? You know Science. That might be in Nature Synthesis. You know, Nature name. You want to publish on that if you're a chemist, scientist, or engineer, right? Those are actually frontier of the scientific research. We are doing that. What's next? What's next is unpublished that you might see on your brochure. Yeah. My group is currently working on making those topological complex structure. If you want to look at one of them, could you pass me that copy since I just yeah. If you open that, those are my lovely group members working, but right in the middle. Yeah. If you want to make a video editing, I can give you a digital copy, so you don't need to zoom.
I zoomed in.
Yeah,
Got
I
it.
zoom in.
Yeah.
Yeah, I'm shaking to that. Yeah.
Oh, can I?
Yeah.
There we go. Thank you.
I'm helping you, Chair. Yeah. You can actually synthesize a small molecule. I erase them, but I can draw them again. For example, in this page, it's a trifoil knot, right? I'm going to draw the trifoil knot quickly on the board. Okay. So this is a trifoil knot, right? This is another method. And rather than synthesize that only, you can have some handles, such as here, right? And just go here, here, and there, right? And I don't need this. And if you connect those handles to another trifoil knot, for example, right? You will still maintain the connections, the crossings or topological structure in the fabric, in the nanoscale. But when you have infinite number of those handles to cross-linking them together, you are generating a 2-dimensional network. Furthermore, if you have 4 of them or in the different directions, you possibly can make a 3D network in nanoscale. And that's a new method, I think, will make way more different types of topological complex structures. Why? If you remember what Jackson talked about, we use denotation and index numbers, right? How many nodes or links does the mathematicians have to find? Don't talk about nodes. Don't talk about links. Only nodes. One segment itself can go easily billions of that. Within the crossing number, just 10 or 11. I can't remember the exact number. When the crossing from 8 to 9 to 10, each type of the node numbers go significantly high, right? You cannot even find, do I find out all those nodes? No, you cannot, there's so many. And currently they are using supercomputer try to solve all those problems. In another word, mathematicians have provided us extremely high amount of possibility for using the structures to build the topological network. And lastly, I'm talking about why we are making those in such a way. They talk about why we use the topological structure in chemistry. It's give you both the robustness and the flexibility. So you can think about how about we move the crossings in each building block, right? As I said, topology is about maintaining the crossing, maintaining the structure, but you can have a relatively motions or changes. So you can think about if we finally make this material, we can change the structure, geometry, or whatever you call, but not changing the connections, which is topology, right? We might have a really big pore in the center of each building block. And those pores can be used like a filter membrane for the water pollution, or the energy harvesting, carbon dioxide utilization, and so on, right? And then you get, let's say, CO2 in the middle, and you want to release those, like a high pure CO2 and reuse the material. You don't need to break this material. The only thing you do is maintain the same topological structure, but change the relative relationship. For example, we keep the tripod knot again, but squeeze that to this structure, right? The pore will be smaller based on the physical law. The gas, whatever you absorb, will be released. And the material itself have nothing changed, only the relative relationship. The topology, the overall connection, whatever, is still the same. So you can use back and forth just using a torch, wash, or whatever, but it's nanoscale. So it's actually not trapping the water, it's trapping whatever highly selective. That can also be used for catalysis and so on. For example, you want to catalyze the active, change like that, deactivate it, stop using that, change the relation to another one. So there are so many possibilities for using those topological compact structures. I think the time is about to done. I can stop anytime, and I can keep talking for ages. And that's really up to you. I want this presentation to be really interactive, hope you can understand the terminology all the way from mathematics and subjects and back to nanotopology about Luna just talked about, then how we make them in chemistry. And feel free to ask me any questions. Feel free to scan the QR code, find more information on our group website, or we even provide some links to the actual literature. You will find, oh, those chemical structures are so complex, I don't want to synthesize those. But yeah, they're pretty fun. I really enjoy working in this field, and I will work on that in the coming years. Oh, you keep eyeing.
Well, thank you.
My student will keep working with me too. Yeah.
Thank you very much, Dr.
My pleasure.
Feng.
Yeah.
You were aiming for about 45 minutes of lecture time. You're around 48.
Oh, okay. Good
So
job,
that
Phil.
leaves about 12 minutes of questioning from the audience.
Yes, please. Oh.
That'll.
Cool.
And if you all wanted to take a group picture, if the audience would like to take a group picture in front of the board, Dr. Feng, would you be opposed to that?
Oh,
or?
okay. Yeah.
Okay. Excellent.
Hope you all enjoyed that.
Yeah.
No magnets because you're dirty now. It's paper magnets.
Oh, watch the tripwire there.
Yes.
Good, man. How are you?
I can take a picture for you.
Oh, really? Thank you. Oh, actually, you can join in. This thing will take video, and then I can just take the picture from that.
That's my major in this, so I can major is film, so I can take picture.
Okay.